Alright guys, so let's take a look at limits at infinity today. And what are they useful for? Well, if you think about the graph of y equals 1 over x, you may have graphed it before, and you know it has a vertical asymptote at x equals 0, but it also has a horizontal asymptote at y equals 0, a horizontal asymptote there. And what that tells you is that the limit as x goes to infinity of 1 over x is going to be equal to 0. So the graph of the function y equals 1 over x is tending towards 0. It never touches it, but it approaches it as x goes to infinity. And the same would be true for x going to negative infinity. So when you go in the opposite direction, you also tend to 0. So that is true. In fact, a little bit more is true. And we're going to use this fact to compute limits at infinity. So fact. This, of course, we have to prove, but we don't prove it. We just take it as a fact. That if n is a positive number, then the limit as n goes to infinity, x goes to infinity, n doesn't change, x goes to infinity, of 1 over x to the n, so now you can raise it to any power, and this could be plus minus infinity, I should have written that as well, is 0. So we're going to use this fact over and over to compute different limits. And this is pretty much all we're going to need. Then after, we're going to have another technique called L'Hopital's rule. We're going to do that. But at the moment, we're going to limit ourselves to this limit. So first example, how do we compute limits at infinity? So let's do something simple. Let's say we want to compute the limit as x goes to infinity of x minus 4 over x plus 3. Just something simple to start. All right, so at the moment, obviously we cannot plug in infinity because we would end up with some infinity over infinity. And at that point, at this point, you don't want to factor, but you want to do some algebra. And the algebra we're going to do is we're going to look at the degree, the highest degree of x on both the numerator and the denominator. In this case, the highest degree, or the degree of the expression, is 1 and 1. So we're going to pick x to the power of 1. And we're going to multiply and divide by 1 over x to that power. And you'll say, why would we do such thing? That doesn't make any sense. But it's going to help us out because when we distribute this out, what we get is that you multiply 1 over x times x. And I'm going to do it in extreme detail this time around. Then after, we're not going to do it. We're just going to distribute in our heads. But right now, we're going to have x times 1 over x minus 4 times 1 over x all over x times 1 over x plus 3 times 1 over x. So as you can see here, x and x will cancel, and you will end up with limit as x goes to infinity of x times 1 over x, which is going to be 1, minus 4 over x. And then here I'm going to have 1 plus 3 over x. But now I can take the limit, because now if you notice, the limit of the denominator is not infinite and is not 0. So I can just compute the limits of the numerator and denominator separately and then divide one by the other. So what this becomes is the limit as x goes to infinity. Remember, you cannot do this whenever the denominator becomes 0, but in this case there's no problem. So I get limit of 1 minus 4 over x over limit. So that's what that allowed us to do, to be able to break it up like so. And now you have to compute the limits. And you notice that this one is the limit of a constant. You're going to get 1. But this right here, due to our fact, our little theorem, this is going to be 0, this term alone. And this term will be 0 as well, because you have a multiple of this limit that we know that is 0. So at this point, the limit on the numerator becomes 1, plus or minus 0, but that's already 0. And then we have 1 in the denominator, where we get that our limit is 1. So we were able to compute that limit by using this fact. All right, let's do a couple more of those, and then we're going to get into, we're going to write a general rule for these types of limits. So let's erase and let's do another. All right, so let's take a look at another example. All right, so this time around, we're going to look at one expression where let's have an x minus 4 again, but let's do an x squared plus 3x plus 1. So now our strategy will be the same. If we were to plug in here, we get infinity over infinity, and that would be a problem. So we're going to have to multiply and divide by x to the highest power that appears both in numerator and denominator. So the degree of the numerator is 1, so that's that. The degree of the denominator is 2, so I'm going to use that 2. So 1 over x squared, 1 over x squared. Why would I do that? Well, my intention is to eliminate all the powers of x and put them down in the denominator so I can use this fact. So that's why I'm picking the largest of all exponents so I can clear them all out. Okay? All right, so then we distribute. And this time around, I'm just going to tell you what happens. You get 1 over x squared times x. You're going to get 1 over x. So x squared, x over x squared, 1 over x. Then minus 4 over x squared. When you distribute that one, now distribute this one, you get x squared over x squared is going to be 1. And then you're going to have 3x over x squared. So plus 3 over x, dividing by x squared. And then 1 over x squared, which is just that. So you distribute each one of them and operate. Now at this point, I will use my fact to eliminate all of the expressions of this form and make them 0. This one is 0 because it's 1 over x. 1 over x squared, n is equal to 2, which is greater than 0. Good enough, it goes. Now here, 1 stays. This becomes 0. And this becomes 0. So in the end, your limit becomes 0. Ooh, I just put an error. I didn't write 0 for this one. So 0 minus 0, which is 0 in the top, and the numerator goes to 0. And the denominator goes to 1 plus 0 over 1, which 0 over 1 is still 0. So you get that that limit is 0. Let's do one more. So notice that the first one, the degrees were equal. The degrees of the numerator and denominator were equal. In this case, the degree of the numerator is less than the degree of the denominator, and it went to 0. Let's do one where the degree of the denominator is less than the numerator, so backwards. And let's see what happens. Then we're going to write our general rule for rational functions. And of course, I've only been doing positive infinity, but I could have done negative infinity as well. So let's do that. And then let's do something here with an x squared minus 1 over x plus 2, for example. So something simple to compute there. Strategy is the same. Look at first, if you would plug in, you would get infinity over negative infinity, which is still an indeterminate form that we don't want to deal with. So what we're going to do is we're going to multiply times 1 over x squared, because that's the largest degree of both the numerator and the denominator. So we do that, and we distribute, I'm going to do it here. We get limit as x goes to negative infinity. And then here I get 1 over x squared. And here I'm going to have minus 1 over x squared. And here I'm going to have 1 over x. And here I'm going to have 2 over x squared. Now, let's see what all goes to 0. Again, I put it in the form that I needed. So this goes to 0. This goes to 0. And this goes to 0. And you notice that the whole denominator goes down to 0. And at that point, then you have that the limit is either going to not exist or is going to be going to infinity. At the moment, we're not going to earn plus minus infinity. So we're not going to determine the sign at the moment. We're just going to say that the limit does not exist. So it's going to be an infinite limit right there. All right, so that we will summarize in the next table. Okay, so let's say that we're computing the limit of as x goes to infinity. These are going to be polynomials of p of x over q of x. These are polynomials, and we will say that the degree of p of x is going to be n, and the degree of q of x is going to be m. So in our previous example, n would be the degree of the numerator, which is 1. M would be the degree of the denominator, which is 2. So n1, m2. So let's take a look at the, let's take a look at the possibilities. All right, so if n is larger than m, situation that we have here, well, the limit I should have given it a name so I don't have to write it all over. I should have called it L, is infinite or does not exist. And how would you check for whether it's positive or negative infinity? You would have to analyze the sign of the function as x goes past all the zeros. So you just pick a number that is large enough, but negative in this case, large enough in absolute value, but negative, and plug it in and get the sign. So if you get a negative number, in this case you would get a positive number. Let's see, positive, negative. No, you'll get a negative number, sorry. If you get a negative number, you say the limit is going to negative infinity. And if you would get a positive number, you say the limit goes to positive infinity. But that is just a matter of checking where your signs are going, not a big deal. Now, if n is equal to m, in this case, the limit is going to be the ratio of the coefficients, and I didn't give them names, but let's say an, bn, where p of x is the polynomial of the form an x to the n plus an minus 1 x to the n minus 1 plus a1x plus a naught. And q of x is the polynomial of the form bm x to the m. I call it m? Yes. Bm minus 1 xm minus 1 plus b1x plus b naught. So the largest coefficient, so in this case, an in our case is the one that goes in front of here, and bm would be the one that goes in front of here. But whenever n and m are equal, then you have an over bn, or bm, but this is the same as n. That's going to be your limit. Now the last case is the easiest. That's the first one we did, or second one we did. If n is strictly less than m, then the limit is 0. All right, so let's write a couple of examples and just use the table so we can do it real quick. And then we'll move to some more complicated examples for probably next video. Okay, so at this point I'm going to write a few examples and we're going to do them rather quickly just to see how we apply this, formula right here, or this table right here. So limit, let's do x squared plus 7x over, let's do an x cubed minus 5, something like that. Limit as x goes to positive infinity of x cubed plus 8 over x cubed minus 1. I don't know, perfect cubes, or sum of cubes and difference of cubes. Limit as x goes to infinity of 3x minus 1 over 2x plus 3. Limit as x goes to infinity of, what have I not done? I think I've done pretty much all cases. I'm missing one. So x squared plus 3x over x plus 2. All right, so quite a few. I got caught up there. Oh well, let me tell you what it said. So x squared over 7x. It really doesn't matter what it says, which is great, because this exponent is a 2. So in this particular case, n is equal to 2. So it doesn't matter what the exponents are, which is great in this particular case, or what the coefficients are. It only matters what the exponents are. Even though I got cut off, is not a problem, because I have that the degree of the numerator is 2, degree of the denominator is 3. So you go to your table, n is less than m, therefore the limit is 0. So no calculation needed, and that's why it was good, because I didn't even need to look at the coefficients. It didn't matter. The degrees gave us already the result. So perfect example for it to happen, so we didn't have to rewrite it. Now this one right here, notice that n, which is my numerator, is 3, m is 3. So I have to do the ratio of the leading coefficients. And who are the leading coefficients? I have a 1 that appears in front of each one of them, 1 times x cubed, 1 times x cubed. So those are going to be the numbers I pick. So it's going to be 1 over 1, and the limit is 1. So that's how easy it is with the table. So all the procedure we did before, you're like, why did we even? Well, we're just trying to motivate the table. Once you know the table, you can do it very easily. Of course, in the next video, we'll do some limits where you cannot use the table. This is only good for rational functions. So, of course, we're going to do that. So now our degrees are going to be 1 and 1. So we're still on the equal sign, equal case. And that is then we do the ratio of the coefficients. Now my coefficients are not 1s. They're 3 and 2. So I pick those. And my limit is 3/2. That's as easy as it can be. And now last one, my n is 2. My m is 1. So I am back to the case when n is greater than m and my limit is infinite. Is it going to be positive or negative infinite? Well, just pick a number that is past all the zeros. The zeros for this one are 0, -3, and -2. So if you pick, for example, x equals 1 would be sufficient. Usually we pick larger numbers, but x equals 1 will suffice. You have that this expression here becomes 1 squared plus 3 times 1 over 1 plus 2. So it doesn't matter what the number is, it matters that it's positive. And then that tells you that this limit is infinite, and it's going to be actually positive infinity, because once the graph of this function crosses the axis into the positive side, it stays positive because there's no more zeros after that, and it keeps going like that all the way out to positive infinity. That's really all is happening right there. All right, so that's quite a few examples, so we'll leave it at that for this video. And next video we'll do a few limits, infinite limits or limits at infinity that do not, or you cannot use the table for, so you will have to do a little bit more math to get them. All right, so until next time, I'll see you